Okay, so a student asked a question about exercise 14.86. This is from Tro, 3rd edition. And it's a little bit complicated, so I'm going to go real slow here. It's maybe a long video. So let me read it out loud first. The reactions below can be combined to make this overall reaction by reversing sum and or dividing all the coefficients of sum by a number. Determine how the reactions need to be modified to sum the overall process. Then determine the value of K for one of the reactions to be combined. Finally, combine all the values of K to determine the value of K. Okay, so first of all, pretty scary, right? Lot there. What I'm going to do is I'm going to go to my notepad and I'm going to make some notes. So it looks like this is reaction 1. I'm going to call that A. There's A right there. So this is reaction A. Here's reaction B. Here's reaction C. Looks like these three together can be summed to make that. So I'm going to write those reactions down first. Reaction A was, I think, C plus O2. You see that? O2, it makes carbon dioxide. O2 makes carbon dioxide. Probably wondering what that sound is in the background. It's my wife trying to run her sewing machine really quietly. She's not doing a very good job, is she? B is 2H2. 2H2 produces, or rather plus O2 gives 2 waters. Plus O2 gives 2 waters. Right? And C is carbon monoxide plus oxygen gives, okay. Carbon monoxide plus oxygen gives, I think that was 2 carbon dioxides, right? Is that right? Okay, let me go back and check that. That's right, okay. So this is 1.363 times 10 to the 69. Times 10 to the 69. KB was 1.4 something times 10 to the 80. And KC was, I think I got that wrong, 1.389 and 477. Okay, 1.477 times 10 to the 90. And just a second here, I got an eraser. 1.389 times 10 to the 80. Okay, great. So now we know that these all combine to form a common reaction. This is all from the question stem. And it was the common reaction, or the overall reaction was C plus water gives carbon monoxide and hydrogen. C plus water gives carbon monoxide plus hydrogen. Okay? And so it looks like we're going to combine these things together to give the equilibrium constant for this reaction. Well, this looks like Hess's law. Remember that? Hess's law? Remember that? That was, I don't know, chapter 6, chapter 5, something like that. Gosh, maybe even chapter 4. So either way, look, if you're going to look something up in a textbook, I think you might want to look that up. And the Hess's law basically goes like this. Hess's law goes like this. A plus B produces C. C plus D produces E plus F. We could sum these two reactions. Then we were saying that, let's say the enthalpy of that reaction was let's say 4, and the enthalpy of this reaction, we'll say, is 5. If we said, if you knew that, I'm making these numbers up, okay? That's a 4 and that's a bad. That's a horrible 5, isn't it? How about a 5 you can read? 5. If you wanted to know what was the enthalpy change for the reaction A plus B plus D produces E plus F, right? Can you see how I'm adding up all of these and these, except I'm canceling out that C? I'm adding up all those reactants, and here's these reactants here, and I'm adding these up, and I'm getting those, okay? So what is the enthalpy of this reaction? It's 9, okay? What would be the enthalpy of the reaction C produces A plus B? The enthalpy of that reaction would be what? Be minus 4. Remember that? Okay. And then the other thing I want to point out here, let me get rid of this thing here. Can I just get rid of it? I don't know how to get rid of this. Here we go. Bam. Okay, so let's put another one here. And say, did you also remember, well, just from reading chapter 14, that K is equal to products over reactants? Right? So let's have a couple reactions here. I'm going to say reaction X will be A plus 2B is in equilibrium with C, let's say 3D, making this up as I go. K, the equilibrium constant for this reaction is going to be the products of the reactants, right? So it's the concentration of D raised to the 3, concentration of C, concentration of A, concentration of B squared, right? All right, so let's have another reaction. Let's say in this case it's 1/2 A plus B is in equilibrium with 1/2 C plus 3/2 D. What would K be? This is K of Y. It would be D, C, I'll put the exponents in just a moment. A, B. Okay, and A would be raised to 1/2, right? B would be raised to the 1, right? Because it's just a 1 here. I'm going to say 2/2 to make a point. Look at that. C would be raised to the 1/2, and D would be raised to the 3/2. Can you see this is the same thing as Kx raised to the 1/2? Right, it's the square root of that. Okay, let's do another one. Z, and you sort of need to know this, or you need to. I mean, we could have known it by looking at the definition of, up here, that the equilibrium constant is defined as the concentration of the products of the concentration of the reaction. We could have known that. We could have known all these things from that. But that it is true, in my opinion, is not necessarily obvious. Let's do another one. Let's say C plus 3D is in equilibrium with A plus 2B. What is the equilibrium constant for this reaction? Please pause the video here and write it out. Okay, let me suppose that you did pause the video, and I'm going to say that is A B squared over D and C. What is D raised to? The 3, right? Okay, can you see that this is Kx to the minus 1? Okay, if you can see that, that's great. If you can't see, please pause the video here and figure it out. Give me a call, text me, look that up. You've got to figure out. It's directly related to that definition right there. Okay, and if you can't get with me right away, then put a star next to it and bring it to me later and ask me why that's true. Okay, but this is very important. You've got to know this in order to be able to solve these problems. Okay, so let me go here. Let's go back over here actually. All right, so if that's true, how are we going to add all these guys together to get? I'm going to go with a different color here. Let's go with green. How are we going to add all these guys together to get this net reaction? I'm going to call this X, okay? So it looks like if I've got C in the reactants and I've got one C in the reactant and one C in the reactant here, then it's likely that this is going to be left alone. So I'm going to go ahead and say that we want to leave this just as it is. Okay? Now look at this. If I've got H2 in the reactants here, 2 of them, and I've got only one H2 in the products, I need to turn this guy around. Right? So I need to multiply this by -1. but I also have got 2 here and 2 here, and I need 1 in the net. So I'm going to say let's also multiply it by 1/2. Okay? That's going to turn this guy around. I'm going to write the new one here now. It's going to be H2O is in equilibrium with, I'm going to call this B prime, okay? Is in equilibrium with H2 plus 1/2 O2. Okay? So what's the new equilibrium constant going to be? It's going to be 1.389 times 10 to the 80 raised to the minus 1/2. Can you see that? Okay. So if this is the case, I'm going to go ahead and write this off so I can see it all in green. I'm going to write this up here too. I didn't change anything there. All right, now that's done. Now that I've got that, let's do what's going to happen here. So again, I've got 2 carbon monoxides in this reaction, but in the net reaction I only want 1. So I'm going to have to turn this around. I'm going to have to multiply it by -1. But you can see this is reactants, this is products, multiplied by -1. I'm also going to multiply it by 1/2. Okay? So Kc prime is going to equal to Kc raised to the minus 1/2. Okay, do you see that? So this is carbon dioxide is in equilibrium with carbon monoxide plus 1/2 O2. Now look at this. This is what I did. I knew I needed to rearrange it so they all added up to this red here, but look what they do. This C is here. Boom. This O2, there's a 1/2 O2 and a 1/2 O2, right? Here's one of the reactants and 2 halves in the products. So those are canceled. Beautiful. Here's a carbon dioxide here in the products, carbon dioxide in the reactants. Boom. Okay. Here's a water in the product, in the reactants, and here's a water in the reactants. Good. Here's an H2 in the products, and here's an H2 in the products, and a carbon monoxide in the carbon monoxide. Perfect. All right. These all work perfectly. Okay. So it turns out this was correct. We had to, the top one we left, we left intact, just multiply everything by 1. The second one, we multiplied everything by minus 1/2. And this, the bottom one, we multiplied everything by minus 1/2. So let's go back here now and look at the question. How does the first reaction need to be modified? And the answer is it doesn't. Okay? So let's come here and, didn't mean to submit. Let's come here and say it is carbon, solid, plus O2. Gas is in equilibrium with carbon dioxide, 2, gas. Okay? And that's what we said needed to be. Let's go back over here. We don't want to do anything to that. Just leave it as 1. Leave it in its place. Okay? Carbon plus oxygen gives carbon dioxide. That's what we wanted. Back here. Yep, that's it. Submit. Bam. Green. Okay. The next one, we said, oh, this needs to be turned around and cut in half. So let's say if we turn this around, it's going to be H2O gas plus, or rather nothing. Yeah, nothing. That's the only reactant. Gives H2 gas plus 1/2 O2. I'm gonna go real slow here because it's easy to get the stuff backwards. So is that half of that? Yeah, it is. It's backwards and half of that. It's backwards and half of that. You see that? Let's submit that. Bam. Okay, and this one was also backwards and half of it. So it's going to be C carbon dioxide, because it's only half, 2 gas. That's the only reactant because it's backwards, right? Is in equilibrium with carbon monoxide, gas, plus O2, gas, oops. Gas. Is that backwards of that? Carbon monoxide, nope, this is supposed to be 1/2. Okay, so that works. Okay, now determine how the values of K for each reaction should be combined. You know, you don't really have to understand this, I think, to get it right, because we saw the the K overall. We sort of developed back here with this page here. We sort of developed how these things are going to like, since we appealed to the definition of the equilibrium constant, so this is going to be a pretty busy ratio if we set it all up. But I would encourage you to do that. I would encourage you to go and add up all of these reactants the way that we wrote them. Let me go back here for a second. Add up all these reactants the way that we wrote them. Or no, not that page. Sorry. Go back here. Add up all these reactants and prove to yourself that if you define, you know what? I'm going to give you a hint of what I'm talking about. This is a little bit complicated, but it's going to be busy. Okay. So if we add all these up, we're really going to have C plus O2, all the reactants, plus 2H2, or rather, we're going with the green, sorry. Right, O2 plus H2O plus CO2 is in equilibrium with, and let's write all the products out, CO2 plus H2 plus 1/2 O2 plus carbon monoxide plus 1/2 O2, okay? So if you wrote this total out, if you wrote it out overall, you would write all the products, or the concentrations of all the products, times the concentration of all the reactants. And it would be a really big expression. It would essentially be this, rather this times that. Okay, let's go back here, and it's this choice right here. Okay, now determine the value of K for the overall reaction. All right, let's go back here. I'm going to calculate this. Go back here. Which one is going to get rid of? I can get rid of this one. Okay, let's go with a new one now. Okay, so the K's were the K, let's get a different color. K overall is going to equal Ka times Kb times Kc, okay, which is equal to 1 point, I think it was 383, 1.363. Times 10 to the 60 times 1.30, I remember the last one, 389. Times 10 to the 80 times negative 1/2 times 1.477 times 10 to the 90 times the negative 1/2. Okay, so I'm gonna do this. I'm gonna simplify this. This is going to be 1.363, because I can't put these numbers in my calculator. My calculator won't handle it. 1.363 times 1.389 times negative 1/2, or raised to the negative 1/2, times 10 to the 80, 1/2, times 10 to the, I forgot that, 60, times 1.477 times, raised to the 1/2 times 10 to the 90 raised to the minus 1/2, okay? This is 1.363 times, I'm going to calculate the negative square root of, you know what, I'm going to do one more step here, just in case you're not sure what's going on here. This is going to be 1 over the square root of 1.389, right? Because that makes it the reciprocal, because it's negative, and then 1/2 is the square root, times 1 over the square root of 1.477 times 10 to the 60 times 10 to the minus 40 times 10 to the minus 45. Okay? Clear. 1.363. Excuse me. 1.363 times okay, so these first three come out to be 0.9516, and these come out to be times 10 to the minus 16. Okay, because 60 minus 40 minus 45. So this comes out to be 9.516 times 10 to the minus 17. All right, let's put that in there and be done with this long video. 9.516 times 10 to the minus 17. Nope, that's the right place. Okay, so hope that's helpful. Try to be a little bit less repetitive in videos than I am in person, so please consider watching it again, parts that you don't understand, or following up with questions with me.